So this is FRQ 10. This is an electrochemistry based question. It's a pretty good question. It goes through a lot of the different parts that you're probably going to see on an AP test. The very first part starts where you're running an electric current through a copper solution. Okay, it gives you some details on it, but the first question just says, what's the reaction that's happening here? What's the balanced half reaction for the reduction? And essentially what you're doing is you're taking the copper 2 ions that are in the solution and you are combining them with electrons as the current passes through, and that's going to then create copper metal. And so you're going to see at one of the electrodes, you're going to see copper metal form, and you can use that to plate or do something like that. Okay, so that's your half reaction that you're looking at. And then the kind of next question gets into some of the thermodynamics of that. Okay, so is this a galvanic or an electrolytic cell? So galvanic cells occur when you have a voltage that's positive, which means that your delta G would be negative. And so you want to kind of link these two things as being synonymous, that having a positive voltage is a thermodynamically favorable process. Whereas an electrolytic, your voltage is going to be negative, and therefore your Gibbs free energy is going to be positive, meaning your reaction is not going to happen unless you provide work. That's confusing because in this case you have a reaction that's occurring, but you're also doing something, you're running electrical current. So which of those two do you fall into? You fall into the electrolytic. So by you supplying current, what you're doing is you're taking something that is not going to happen on its own, and you are forcing electrons upon it. And so you're doing something that's making something that's not spontaneous happen. Now, spontaneous doesn't mean whether or not it can happen. It says whether or not it can happen without an input of work or without an input of energy. And so this is an electrolytic case, and that's confusing in the sense of the voltage, but it's not confusing in the sense of the Gibbs free energy, I think. And so that's kind of where you want to make your case. You're supplying electrical current, you're supplying a voltage to this in order to get this to happen, and that's forcing these electrons upon that ion. And so therefore that would be an electrolytic cell. Now, probably the kind of meat of this question gets into part C. So in part C we're doing a little bit of coulometry, okay, which is tricky. So before we start, a couple background things. One electron has a specific charge, thank you Robert Millikan, 10 to the 19th coulombs, 1.6 times 10 to the negative 19th coulombs. And that is something that we were able to measure very precisely, although not initially. But we now know very well, and very soon after we had kind of said that the experiment, it quickly evolved into that number. And then what I can say is then, if I had a mole of electrons, if I had a lot of electrons, I would have approximately this many coulombs of charge. And that number is called the Faraday's constant. It's often treated with the symbol F, and on your AP test it has the little cursive F, big cursive F for the Faraday constant. And then the last thing that's important to know is that coulombs is a unit of how much charge. How much charge do your electrons carry with them? And as that charge flows, you can say how many charges are flowing past a given point in a second. That's equivalent to an amp or an ampere, something along those lines. Okay. So in C part 1, it says that you run current through a solution for 3 minutes and form 0.0832 grams of copper. And it just says how many moles of copper formed. Okay. So just a quick conversion. 63.5 grams of copper is 1 mole, and we get 0.00131 moles of copper. Is our answer to part 1. Part 2 says how much charge did it take to accomplish that? And the idea that's getting at then is that my first equation was copper 2 plus 2 electrons turns to copper. In order to make a mole of this, I need 2 moles of electrons. Okay, so I can do a calculation where I take this answer here, this 0.00131 moles of copper, and I can do a stoichiometric conversion between copper and electrons by saying this. Each mole of copper required 2 moles of electrons. And then I can use my Faraday constant to convert that into charge. 1 mole of electrons possesses 96,500 coulombs, or something close to that. I think that's rounded quite a bit. Nonetheless, this comes out to be about 253 coulombs of charge. Okay. Which makes sense as an answer. That's significantly less than the Faraday's constant, which makes sense since we have less than a mole. Okay. On part 3, they then link that together, and they then say, what's the current running through your solution? So to get the current in amps, you need to compare how much charge versus how much time. Okay, the equation that you're going to find on your sheet is current is equal to charge per time. And that's not the Q in heat or specific heat capacity. This is charge. It's a physics unit. The units on these amps are current, coulombs for charge, and seconds or whatever for time. If you want amps, you would do seconds. Okay. So what I can do then is I can take my 253 coulombs, and it runs for 3 minutes, which is 180 seconds, which comes out to 1.40 amps of current that are flowing through that. Okay. And that's probably one of the first ways we could actually measure what the R constant was using coulometry. It worked very well. All right. The last part, we're going to get into a little bit of engineering here. When you're making a battery, what's happening, what's going on? So you're presented with this picture, copper chloride, zinc chloride, says what's missing. So the problem that happens in this particular battery, here we have the zinc metal is becoming zinc 2+ ion, the copper 2+ ion is becoming copper metal. And as that process occurs, electrons are going to move from this zinc metal over to the copper metal electrode, where they're then going to combine with the copper 2. So as electrons are moving over here, they're moving over there because they're attracted to the positive charge in the protons in the copper 2 ions. So the copper 2 ion in here has a force on the electrons that are present on that zinc metal, and that allows the electrons to move from the zinc metal over to here. So I'm pulling on it, I'm putting a force on it, and it's from the protons, and of course there's repulsion as well. But the net effect there is that electrons will move from this one side to the other. And the more force I can apply, the more energy these electrons will gain, so I get a bigger voltage difference. Okay. So what the problem is that over time, if I start to just run electrons over from one side to the other, then I would accumulate positive charge over here and negative charge over there. So then the next electron would see all this excess negative charge. Well, now there's more repulsion, and so it's not going to be able to have a net force over there. So very quickly this would shut down. So in order to fix that, what I need to have happen is I need to have a salt bridge. And a salt bridge is just a little construction where you have like a slurry of salt ions. Any salt will work. Potassium nitrate would be one you could use. And as the electrons move, the anions in the salt tend to drift towards this side, and the potassium ions tend to drift towards that side, so that the total charge remains constant. And what that does is that maintains a neutrality that allows the continuation of the flow of the electrons. Without that, then your cell is going to shut down because it's going to have a net charge on one side. It's going to force a very quick equilibrium where the force no longer was pulling electrons over. Second question says, what's the voltage? And so here we're taking the copper 2 to copper, which was positive 0.34 volts. And we're going to flip the second reaction. And when I do that, I'm taking the zinc metal from the zinc ion from being reduced to the zinc metal being oxidized. So it's the opposite process, and so the energy gain from that is going to be opposite as well. So I'm going to change my sign to a positive. And I'm just going to combine the two. 1.1 volts would be the voltage of that cell, as long as my concentrations are at standard conditions. Okay. Why does the reverse reaction not happen? There are quite a few answers you can give to this. I'm sure there's lots of acceptable things we could say, such as, your voltage is negative, which means that your Gibbs free energy is positive, so therefore it's not spontaneous. You could also do a physical explanation. These electrons are more attracted to the copper 2 ions than they are to the zinc metal, so therefore the reaction run in reverse doesn't make any sense because there's more repulsion than there's attraction. I think any of those answers is fine. And it's kind of hard to draw a line between what's right and what's wrong. And then the last question is a difficult one. It says, why when your battery starts to run for a long time does your voltage eventually change? And I don't think that's as simple as people make it out to be. Of course, as your battery runs, eventually it's going to die because the chemicals are going to run out. But in the meantime, you will see a shifting of the voltage. There is a physical explanation for that I'm not too sure of, and I haven't been able to find anything else. And then there's also kind of a shortcut explanation that really doesn't explain what's happening, but it gives you an answer. The shortcut explanation kind of relies on taking things that we can use for other systems and applying it towards this, which I don't know the significance of how valid that is or not, because I don't really have a keen idea of how this works. But essentially, the copper 2 and the zinc 2 plus are the only equilibrium, things that matter here. The solids are going to be irrelevant as long as they're present. And so as the concentration of your copper 2 is going to decrease over time, and the concentration of this is going to increase over time as the reaction proceeds, that's going to change your rates of reaction, which is going to cause a shifting to achieve the equilibrium. I don't really like that explanation. That's something along the lines of what the AP people are looking at. And if you're watching this and you're better at this than I am, feel free to leave me a comment. In my head, what's actually happening is this. As I'm losing zinc 2 plus, or as I'm increasing the amount of zinc 2 plus ion, I'm getting more and more positive attraction to that electron. And so it's not gaining as much energy as it leaves because of that. And so its voltage is decreasing. Likewise, this electron is attracted to these copper 2 ions. The fewer of them there are, the less and less attractive force there is. And so physically, I think it makes sense to look at that, but then that leaves a lot of questions. Does this have to be uniformly distributed, or can that copper 2 be anywhere? Why do the numbers work out the way they do for 1 molar? Why do they work out the way that they do for when we change those concentrations? I don't think I have clear answers. But there is an effect on your voltage as your concentrations change. And I think that would be good to know, even if the answer as to why is kind of vague. So that's electrochem. That problem encompasses most of what you're going to see in the test. Probably a little bit of chemistry in the battery would be nice to add, but that's about it. Okay, if you have any questions, post, and I'll do my best to answer.